So this will be, the last talk of the morning. So it's my pleasure to introduce Achill Schurmann, who will talk to us about a Simplex-Type Voronoi algorithm.
Yeah, thank you very much for the introduction and for inviting me. I'm very happy to be here and learn so much this week. Was very nice, and I'm also very happy that Wessel gave already parts of my talk, so I can go fast over the first few notions. Actually, I can jump directly from lattices to quadratic forms or gray matrices, and you know already what perfect gray matrix or perfect form is. The minimum, the arithmetical minimum is the squared length of a minimal vector, and so I will do everything in the language of gray matrices and quadratic forms because Wessel already did the job for jumping there. A little bit has to be said here because my n is his d. There's a little bit of a difference. But other than that, we have similar notions. Q is supposed to be positive definite, and then we have a perfect Q if and only if it is uniquely determined by the arithmetical minimum and the representatives, so the minimal vectors. And he also had the notion of a Voronoi domain, which I call Voronoi cone, and these are full dimensional if and only if Q is perfect. And then there's this classical theorem by Voronoi, which tells us that these Voronoi cones give like a nice tessellation of the cone of positive semi-definite or positive definite matrices, and there are only finitely many up to GLNZ equivalents. So that's kind of a short version of the introduction by Wessel to remind you. And Voronoi was actually interested in reduction theory for lattices or quadratic forms in this case. And from these Voronoi cones you can obtain like a fundamental domain by splitting it up to the action of GLNZ on the space of positive definite quadratic forms. So the base changes in lattices correspond to these jumps here in the space of positive definite quadratic forms from form Q to an equivalent form U transpose QU. Right. And now the idea is to adapt this algorithm of Voronoi, which Wessel talked about, to get certificates for some form lying in one of these cones. So I want as an input matrix some quadratic form or gray matrix lying somewhere, and then I want to find the cone which contains that. And I can adapt this Voronoi algorithm to find this cone in a simplex kind of way. I go from cone to cone until I find this corresponding Voronoi cone. In this classical setting, this doesn't make much of a new thing, because it's basically giving a certificate for something being positive definite, but there are other ways to prove that something is positive definite by computing the eigenvalues, etc. But we want to do this in another setting for other cones. So I want to generalize this somehow. And I also want to generalize this notion of a Ryshkov polyhedron, which Wessel mentioned, which is used to kind of do this search of cones. It's a dual picture to the Voronoi cone picture, and the vertices correspond here to these perfect forms, and then the Voronoi algorithm can be seen as a graph traversal search on this edge graph of this Ryshkov polyhedron. So vertices correspond to perfect forms. You start with one and then you explore this graph until you don't find any new ones. And as he said, there are a lot of shortest vector problems to be solved in order to see, for instance, what the facets are locally, and in order to find neighboring vertices, you also need a lot of shortest vector problems. Then you test whether or not this is already known. This is a lattice isometry problem. But actually the bottleneck in this classical setting, as he mentioned already, is this polyhedral representation conversion. So given facets of a polyhedron, find the generating rays. So this is kind of a classical important problem in combinatorial optimization or combinatorial polytope theory, and this is actually the bottleneck here, why this doesn't work in dimension 9, 10, etc. So shortest vector problems is not such a difficulty here, but in our generalization it will be. And that's actually the reason why I give this talk here, because there's a version of the shortest vector problem which I can't solve quickly, and I thought this might be the audience where some people have ideas how to solve that in a better way. Okay, so this is the reminder of what Wessel talked about already. If you have any questions up to this point, I'm happy to answer that.
Yeah, so for 2, you're saying that this is the bottleneck in this algorithm. And is that just because there are many, many facets, I guess exponentially many, or it's just...
No, the facets are the number of minimal vectors, but the problem is there are these high-dimensional highly symmetric lattices like the E8 root lattice, and then you have, in these cases, polyhedra which have a lot of generating rays, even up to symmetries. And in dimension 8, the main objective is to find like these generating rays of the E8 polyhedron, so to say, which has 120 facets because there are 240, so 2 times 120 minimal vectors, but an enormous amount of rays, even up to symmetries. And Mathieu has like special code for computing rays up to symmetries and has developed over the years some techniques to kind of solve these problems, so we were able to do this up to dimension 8. But okay, that's the old story. We want to generalize this now to a setting where I replace the cone of positive semi-definite matrices by other cones. So in particular, I'm interested in this completely positive cone, which is kind of a part of the positive semi-definite cone. So instead of looking at the cone generated by all these rank 1 matrices, I just take those which have non-negative entries here. So positive semi-definite would be the cone which comes from all vectors x, and now I'm just taking a subcone here. So in this 2-dimensional picture, n equals 2, we have simply the half of this 3-dimensional cone. And it's still split into Voronoi cones. And the dual cone becomes bigger. It's called the copositive cone. And now generalizing this Voronoi algorithm works by having a decomposition into Voronoi cones in this small cone and a Ryshkov polyhedron in the dual cone. So kind of you split into 2 worlds, so to say, which were previously in one cone. In the semi-definite case, we just work in one cone because this is self-dual. So in order to generalize, we now need a notion of copositive minimum, etc. So, but let me tell you about an application first, or why we are interested in this. So this comes up in copositive optimization, which is kind of a conic optimization problem, a class of convex optimization problems which generalize linear programming. So this is like a linear programming standard form where a cone for linear programming would be the non-negative real vectors. And if we replace this cone by other cones, we get things like semi-definite programming or copositive programming, which is obtained when we take this cone to be this cone of completely positive or copositive matrices. And one difficult thing there is to give like a certificate for something to be copositive and or completely positive. And we want to use this Voronoi adaptation to prove that a given matrix is completely positive. So we want to give like a certificate for a given input matrix, say A, we want to write it like a rational rational linear combination of rank 1 matrices.
Which are
Sorry?
non-negative.
Which are non-negative, so X should be a finite set of non-negative vectors. Right. So we're looking for something like that. This can be used as a certificate that something is completely positive. And that's exactly saying this is living in a cone like these Voronoi cones. So, okay. So we need to generalize the notion of minimum, the notion of perfectness, the notion of the Ryshkov polyhedron now to this copositive setting. And this version of the shortest vector problem I was mentioning is this COP SVP, so the problem of finding the copositive minimum of a copositive quadratic form. And this is quite difficult to compute. Deciding whether or not something is copositive is already co and p complete. So far we don't know exactly what the difficulty is, and we only have a very naive bad algorithm to solve this at all. So based on a result by Bunfus and Dürr, we can kind of split the problem into a finite number of classical shortest vector enumerations. So what we do is like we take the standard simplex, so which is kind of generating set for the non-negative ortant. Then we can like look at it, and if on this simplex the input form is non-negative, we can do an enumeration. If it's not non-negative on this cone, we have to split this cone and find a subdivision on which this is non-negative, so to say. So for instance, if we have E3 transpose times Q times E2 less than 0, then this condition of being non-negative on the complete cone is not satisfied on this edge, and we therefore split the edge here and have two subsimplices. Now we check with the new vertex here if the two subsimplices are having this property that it's non-negative. If it is, okay, we can do a classical enumeration shortest vector problem there. If it's not, we have to split further. So maybe we take a point here and split this into simplices, and we have some flexibility in how to split. But the problem is that for general input, this kind of splitting is very intense. So there is a lot of splitting, super exponential many, actually. Yes?
Do you need this computation to be done during the preparation of the certification or the verification of the certificate?
I will show you the Voronoi algorithm in a second, where we use this, and this comes up in all kinds of steps there. So if you find a neighboring cone, you need this shortest vector problem. So it's kind of like the motor for the whole Voronoi algorithm.
Would you tolerate that this algorithm make mistake from time to time or not at all?
No, not at all. So we want exact.
But it would be good to have some way to get to that bottom resolution.
Okay. So my main question to the audience is, can we find a better algorithm for this shortest vector problem? Because this is the motor for our certificate algorithm, which I show you now. Yeah, so this is kind of like my add-on to the open problem session.
And, I mean, you should be able to like reduce it to some extent to some integer program. That's not good.
haven't managed to do it, but I'm sure you could. There must be some better ways, I'm sure. Yeah. So this notion of perfectness and the Ryshkov polyhedron we can generalize simply by, instead of saying that the arithmetical minimum should be greater equal 1, we just replace it by the copositive minimum being greater equal 1, and perfectness is defined over this copositive minimum. So something is called copositive perfect if and only if it is uniquely determined by the copositive minimum and the vectors attaining it. And then we again get like a locally finite polyhedron, like this Ryshkov polyhedron, which is a little bit different because now we have sometimes rays which point to nowhere, so which we call dead ends, which are giving facets of the dual cone sometimes. But we have that perfectness is again equivalent to being a vertex there. And what we want is really a Voronoi algorithm now, completely the same as in the classical case with these notions. As a starting point, we can take this lattice or quadratic form coming from the AN root lattice. It's easy to see that this is a co-perfect thing because the minimal vectors are non-negative. And so we have a starting point in every dimension. We have a Voronoi cone. And if our input is in there, we are done. If it's not in there, we do this Simplex-Type jumping to the neighboring cones. And the algorithm now looks like that, the Voronoi Simplex-Type algorithm. And here, now the copositive shortest vector problem is really the bottleneck. Everything else is kind of easy peasy, but this is the real problem computationally. So we need it in order to find this local situation, to find the facets of the Ryshkov polyhedron at a given vertex, and we need it to find the neighboring vertices. And there it is used extensively, several of these computations. And
are we talking about?
even dimension 6, 7, 8, it becomes difficult.
For the COP-SVP step.
Yes.
Does it help you that you want to somehow solve it over the integers? Like, I mean, if you needed to certify copositivity over the reals in 6 dimensions, is that somehow harder or easier than? Because here you know that your forms are generated by integers because they're vertices of this thing.
Right. I mean, it helps in the sense that we can use like this classical enumeration techniques to just go through the integer vectors, right? We don't have to check all the real vectors. But still, I mean, enumeration is already painful, and if we have to do this enumeration in all of the simplices, in all of the simple cones, it's becoming too much in practice at the moment. So I bet there are easy ways to make this faster heuristically and with a lot of tricks known from the shortest vector community. But I'm not an expert in this, so that's why I'm proposing this as a problem here. Yeah, there's again a polyhedral representation conversion which tells us which directions we can go, and actually there, like in the classical simplex algorithm for linear programming, we also have some choices. We can go different paths. We don't have to take one specific cone, but sometimes we have choices to make, and it's not clear which choices are best. Like in the classical linear programming, we also have the problem of not knowing what kind of pivot rule, what kind of neighboring rule is good. Okay, let me explain this algorithm on a few little pictures. It's maybe easier than looking at just the text. So the interior cases, as I said, is simply solving these shortest vector problems and then finding a neighboring cone until you hit your input. So in this case, after one step, one iteration, we are done. And then the certificate that the input is completely positive looks like that. A little bit more difficult are the boundary cases, and actually we are giving the first algorithm, I think, that gives a certificate for any input that has a rational decomposition. And for the boundary cases, it is not clear which kind of pivot rule leads you there, but by going to a breadth first search, you can at least guarantee that the algorithm terminates at the boundary at some point. So we have a first algorithm for giving certificates in case there are rational CP factorizations. So you write the rational input like this. For the exterior cases, we are still missing a proof that our algorithm ends with a certificate, but we believe that also for input matrices which are not completely positive, our algorithm gives like a certificate after some time. Namely, it ends with a perfect form which has an inner product with the input matrix which is negative, proving that it's outside the dual cone. In practice, this works well, but we don't have a proof that this always works so far. So I'm having a student who currently looks at that. So let me resume with some open questions and to-dos. So we are looking at these pivot rules. That's one obstacle. But one main thing in order to speed up practical computations would be to have better ways of obtaining these shortest vectors for the copositive case. So that's really the main open problem in this field, I think. Yes, and that's the end. I'd like to thank you for your coming, and yes, if you have questions, I'm happy to answer.
General question. For perfect or co-perfect forms, so you're interested mainly in the analysis by the min q, but the number of times this min q is
Old?
Yeah. So let's say if I go to the geometry, I'm interested by the packing density, but also by the kissing number. Now, we don't know how the kissing number is behaving with the density here. Can you say something about if I take perfect forms or co-perfect forms? What can we say something about the number of times the minimum is achieved and how it increases with the dimension?
Yeah, I think the kissing number will give you an upper bound because you can always like extend to a lattice and
Is that clear though?
take the classic. No, it's not.
It would be much smaller than.
Yeah, that's true.
I mean, for general lattices, we know from the tables that it is increasing and probably exponentially increasing. So the kissing number is compensating what the density is doing. Yeah,
So I would assume there should be a bound like that in terms of the classical kissing number, but we don't have it.
If I consider just perfect forms, can I say something about this? Since in the general case I cannot, this is my question.
Yeah, I don't know. So this setting is brand new. And we haven't thought about it, but there should be similar bounds as in the classical case, like kissing number bound, like a bound like Wessel proved for the number of perfect forms maybe.
There's a similar question, like, is there some kind of Minkowski's theorem here?
Like a Minkowski theorem, the classical Minkowski.
Yeah, can you bound that there's, can you bound the minimum in terms of the determinant or something when you're only allowed positive coordinates? Or Minkowski's proof doesn't go through.
Probably yes. I don't know. The problem here is that we don't have like a reduction, right? There's no group action, so there's something different. We don't have like, there's a basis which has small coordinates or something like that. But other than that,
Is there any like obvious symmetry group for these things? No.
Semigroup.
Sorry.
Semigroup.
well, there's this coordinate permutations, but that's just a finite group and not as much as GL and Z. I mean, it's an interesting problem to generalize notions from the geometry of numbers in this setting, maybe. Look how far you can generalize. Yes. Interesting thought, which I didn't have so far. Thank you.